Let me bring you back a little bit to logistic regression, and this is a cost function for logistic regression. Taking the derivative of the cost function, what you get is this, and this is the same as the derivative in linear regression. In neural networks, the cost function is very similar, except that you have another sum for k from 1 to capital K here, and that is the sum cost for k classes for each training instance. The regularized cost function has an additional term, which is the sum of square of all possible theta L I j. So all the parameters theta are included in here except theta naught. The first sum, the most outer sum, covers all the layers from layer 1 to layer L-1. The second sum runs through the nodes in layer L here, and SL is the number of nodes in layer L, and the last sum runs through nodes in layer L plus 1, and should start from j equal to 1, and SL plus 1 is number of nodes in layer L plus 1. We first look at the non-regularized cost function and let unit cost for the instance xi, meaning the ith instance of an output node, unit cost. So unit cost is simply the expression inside the two sum in the cost function. Taking unit cost for k from 1 to capital K, meaning for all the output nodes, and then another sum for I from 1 to m, and m is the number of instances, then we get j, right? J, which is the cost function. And here we make the notation a little bit simple, and unit cost is equal to just this without the subscripts. Now take the derivative of the unit cost with respect to z, and z is the weighted sum at the same output node. So taking the derivative with respect to z, what we have is this. And notice that h is actually 1 divided by 1 plus e to the negative z, and z is this. Z is theta transpose times x. So follow several steps. What we get to finally is this. So the cost for the instance xi of an output node is simply the value of the hypothesis with respect to that instance and the target value. So for example, if the hypothesis is 1 and the target value is 0, then the cost is 1. And if the hypothesis value is 1 and the target value is also 1, then the cost is 0. Now we need to compute the derivative of the unit cost function with respect to each theta. We have theta for layers starting from 1 to layer L-1. So first we look at the output layer L. And here, to make things more easy, I use k for the index of nodes in the output layer, j the index of nodes in the hidden layer, or if you have more than one hidden layers, then you also use j, and I for layers just before this layer, So using a chain rule, the derivative of the unit cost with respect to theta L-1 kj is equal to the derivative of the unit cost with respect to z lk times the derivative of z lk with respect to theta l minus 1 kj. So this is the illustration. Theta kj, theta l minus 1 kj, connecting kth node in the output layer to the jth node in the layer just before it. And we denote the first derivative delta lk, and the second derivative is actually a l minus 1j. That is because z at layer L for node k is equal to theta l minus 1 for the layer just before it, node k transpose times a l minus 1, which is also this. So if you take the derivative with respect to theta l minus 1 kj, then you have just the corresponding a left, right? A l minus 1j left. That's why we see that here. And also following the previous page, delta lk, which is the derivative of the unit cost with respect to z lk, is actually h evaluated at xi minus yi, and this is the error that the output node k in the output layer L made given the ith instance. So given the instance xi, and this is the hypothesis, the corresponding hypothesis, and that is the target value. The difference between those is the error. Now we continue going backward from the output back to the input. For the hidden layer or layers, the partial derivative of the unit cost with respect to theta at layer L connecting node j in L plus 1 to node I in layer L. So here we use the same chain rule, right? We take the derivative of the unit cost with respect to z at layer L plus 1 node j times the partial derivative of z at layer L plus 1 node j with respect to theta at layer L connecting node j in layer L plus 1 to node I in layer L. The second derivative is actually just this, because we have this. We have z at layer L plus 1 node j is equal to this, and that can be written in the sum format. And if you take the derivative with theta lji, then what you have left is just a li, and other terms in the sum are gone, right? So this is what you have left. And here you let the first derivative and you call it delta L plus 1j, which is the error of node j in layer L plus 1. So similarly, you apply the chain rule, you have this. And following the notation above, the first derivative in the sum is actually equal to delta L plus 2k, which is the error that the node k made, the node k in layer L plus 2 made, L plus 2. And if you do this again and again until L plus 2 becomes L, right, then the error, the output node made at the output layer is simply the difference between the hypothesis value and the target value. Now in the next page, we continue to expand this term. Basically, we expand z at layer L plus 2k. That is actually a sum of theta at layer L plus 1 kj times a at layer L plus 1 j. So theta at layer L plus 1 connecting node k in layer L plus 2 to node j in layer L plus 1 times a in layer L plus 1 node j, and sum for all j. And the output a at layer L plus 1 node j is actually a nonlinear function g of z L plus 1 node j, right? At layer L plus 1 node j. So taking the derivative, what we have is g prime of z L plus 1 j times the sum, and in the sum what we have is this delta at layer L plus 2 node k is still there, and also we have theta L plus 1 kj, right, this term. And then we finally write the sum in the vector form, and what we have finally is this. What is the derivative of g? If we take the derivative of the function, of the sigmoid function, then what you get is g times 1 minus g. So basically, if we rewrite the derivative of g, then we have this, and we have this. And g of z L plus 1 j is actually the output, right? The output a L plus 1 j. So finally what we have is this. So in this page we adjust the layer index a little bit to make it simpler, nicer. So the error that node j in layer L made is this, and the derivative g prime is actually here, and it is equal to the output of the same node times 1 minus that output. So from there we get to the backpropagation algorithm, and this is layer level. We first measure the error made at the output layer for all the output nodes. And then we go back to all the previous layers, starting from layer L-1 back to layer 2, and compute all their errors made at that specific layer for all the nodes. So delta L here is a vector containing all the errors made at layer L for all the nodes in that layer. And this is what we saw before in the previous slide. And finally, this is the algorithm for the gradient of the cost function. We need a gradient for a gradient descent. So starting with this, we let uppercase delta at layer L. We initialize them with all 0 for all the layers from 1 to L-1. And then we have a loop for each instance in the training dataset from 1 to M, right? From 1 to M. So for each instance, we apply forward propagation to compute all the outputs, AL, all the output at layer L for all the layers from 1 to L. So in layer 1, A1 is actually just the instance itself with all the attributes. And then we apply the Backpropagation algorithm to compute delta L. And this is the algorithm in the previous slide, with L from capital L back to layer 2, and then update delta at layer L by the partial derivative of the unit cost function with respect to the individual theta. Then this is done for all the layers from 1 to L minus 1. And finally, after the loop, you get delta for layer L divided by M, and it is the non-regularized cost function derivative with respect to theta for layer L, and this is the regularization term. So if you use the if you don't use the regularization term, then the derivative is just this. And what otherwise you take an additional term, it is equal to delta times theta at layer L.